homework is posted due on Monday, and some instructions there. So it has to go through the case study example from the chapter 16 in a couple ways, kind of reproducing some of the things that they did in the book, but then looking at it with mixed effects models. And so I think there's a couple different ways to look at that. And so it gives kind of an idea of some of the models that would be fit in there. And this is a write-up about the project. It includes most of the information we talked about before, but it's written down and posted. It's written on here that either do, when you do the presentations on December 10th, which is the date that our final's scheduled for, and there's 2.5 hours at that time, and so everybody can have 10 to 15 minutes, and then, so there's more time to present details and things. The usual default thing will be pick a data set and analyze it and use some of the methods from the second half of the class. Those could include the linear regression, multiple linear regression, but it could do different types of analysis of variance. You could look at logistic regression that we're going to do shortly, or some other things. And if there's a particular statistical method or thing you want to investigate that employs a different model than we've done or compares procedures, that's fine. There's a few variations that are there. They include developing a lesson plan for primary or secondary school, doing a biography or reading an article in a magazine or journal and reporting on that. And so the way things like a biography or a lesson plan can go, at primary or secondary, you're not going to talk about all the details of a more complex model, but you could illustrate kind of the basic components that go into data and some models. But you might show as part of a lesson plan, well, here's a more elaborate example. So you might do some more plots and some different things. So it could analyze a data set that then is used for illustrating more advanced methods, kind of saying, here are some things you can think about. Oh, and look what we do, later, that type of thing. So it can connect to our class and be relevant. Right? There's not a whole lot of time. There's kind of next week, and then the Thanksgiving week, and then we wrap up. So there's really 3 weeks to go. It's coming up pretty fast. Where is November gone? So figuring out something to do during this weekend, during next week would be great, because then you'll have more time to work on it and ask questions. If kind of by the last week of class you have a draft of the presentation or project write-up, I could look at it that week or over that weekend, and these are due on Tuesday, so you could do some last-minute editing. If I give you some suggestions, but that's an option for everybody. And we're going to go on now and talk about some things with count data. So one thing we emphasized at the beginning of the class is that we're looking at models for data and how to estimate things in the models and how to interpret them. And the models, so down here, models for data. That different types of data have different measurement qualities. They're either discrete or more quantitative and continuous, and the type of models that we use and the things that we do reflect that. So probability models for discrete data have probabilities at certain points, and if we can record our counts or proportions and things like that, then generally we want to use models that are appropriate for that. So for instance, for binomial data, in a binomial type data experiment that has n trials or n survey responses from n people, and p, generally these are independent trials, is part of the model, right, that they're independent. P is a probability of success or recording some outcome, some categories. I've wondered what word would be good to describe that, the probability of something happening, a yes or no, some indication. And then the trials generally are binary, dichotomous. Binary or dichotomous. You're recorded either as 1 or 0, success or failure, yes or no. And so under those type of assumptions, the probability that you have a certain number of successes under that probability model is n choose x, p to the x, 1 minus p to the n minus x, the binomial probability formula. We're a little space there. N minus x there. And those occur at points 0, 1, 2, right, up to n. And so it's probabilities at certain points. And we still want to do confidence intervals for p, or if we have two groups, do the differences, and so on. And so some things might work with the probability formulas explicitly, but at times, if the sample size is larger, we can approximate these probabilities with normal curves or other continuous curves. And so many of our confidence intervals are motivated out of that approximation. Right. And so our actual probabilities, of our values of x, going here 0, 1, 2, up to n. There's probabilities that x equals these values. They might be kind of small at first, right? And then increase, through this range, and then come back down here, something like that, right? So these could be the binomial probabilities, right? But if n is large, generally if n times p is greater than 10 and n times 1 minus p is greater than 10, so we don't have too many failures, we don't have too few successes, right? Then x is approximately distributed as a normal distribution with n times p and n times p times 1 minus p as a variance. And our statistic, p hat, which is x over n, p hat is approximately distributed as a normal centered at p, and its variance is like p times 1 minus p over n. And so we can often approximate these discrete probability functions, these probability mass functions, by kind of a normal curve that would say, here's a normal curve that matches up to that area pretty well. And so taking integrals, taking the area under that normal curve can get a pretty good job of representing the probabilities. And so some of our models for discrete data employ things that are the exact probabilities, and sometimes the models will say sample size is large, so we can do something like normal. Right. And let me clean this. This is p times 1 minus p, and both of those got a little messy. This must be 1 minus p. This is 1 minus p for the variance, right? So there's another issue in general, right? That if we have data come to us from different sources, and we can say different things based on different sources of data. Sometimes we'll have a randomized experiment. And sometimes you can say something about certain proportions, a certain proportion of disease in one group or another. Right? And sometimes you'll have observational studies. And sometimes in those you can say about other things, right? In randomized experience, you can't necessarily estimate the proportion of one group based on what you have in the sample, because it's often a designed experiment with 50-50 right, in the population. A random survey of the population, though, you might be able to say about other things. However, the observational study doesn't use randomization, so it's harder to say, prove causation. So there's limitations of both, and we'll try to keep track of some of those things. Right? So what I thought we'd do today is go through a couple of the methods for inference, for proportions, 1 or 2 samples, and then talk a little bit about odds, right? And see how it goes in terms of our timing. So if we have in trials, independent trials, and X is our number of successes, right, and X has a binomial distribution, right, with the assumptions that go under that, our basic question is, what is that proportion? The book uses pi instead of p, and you could write that. I'm just used to writing it this way. I know I'll drift back into it. Well, if n is kind of large, as described before, the sample proportion is roughly distributed like a normal random variable centered at p with variance p over 1 minus p right over n. Right? And so that ends up meaning that if this is true, if that's pretty accurate for the distribution, if you subtracted p and divided by its standard error, subtract its mean, divide by the square root of that, p times 1 minus p over n. Right? That's like a standard normal random variable. Right? In 252, we've talked about how this is something called a pivot, that there's, this doesn't involve any parameters, it's a distribution we know about. So the probability that negative 1.96 is less than z is less than 1.96 is about 95%. So one rationale for coming up with an interval for a proportion is to take the p hat plus or minus 1.96 times the standard error. But of course we need to do something because p is also down there. So the more simple plug-in approach to making a confidence interval, right, is p hat plus or minus 1.96, and then just plug that same value into here as the standard error, right? And then that ends up being our report for the interval. Right? And that's usually what's presented. Right? There's a slightly more involved way that intervals can be done. Right? This is our value of z, and it's between these two things. Right? And so somebody named Wilson back in 1920s or 1930s said, well, if p hat minus p, if this is true, right, if that's going to be our 95%, we really have kind of two separate equations. We have this lower one and we have this upper one. And we can actually solve for p, right, here to produce intervals that are have two intervals up here that involve p hat, and it's a little more involved to write down this formula, and I'm not going to write it all down. But the proportion test command in R, where you put in x and in, would use that method for coming up with a confidence interval. And if the sample sizes are kind of large, there won't be much difference, maybe in the third or fourth decimal place. But at smaller sample sizes, it can make a little bit more of an impact. And so doing confidence intervals in R, let's do one numerical example, and we'll come back to this, right? So let's say we have a study of 1,000 women, right? And we're asking women who have given birth, and we're asking how many of them, what percent of them had cesarean sections, singleton births. And then asking how many of them had cesarean sections. Now, if there's complications Maybe singleton births, term deliveries, right? If there's emergencies or complications or multiple births of twins, triplets, and things like that, then C-sections are more likely. So these have gone to term and they're singleton. What percent are having C-sections anyway? And let's say that 309 out of the 1,000 have had that. So our estimate of P is that ratio, 0.309, and we want a 95% confidence interval for P, kind of the probability of a C-section in this group of women. And when I first started using this example a few years ago, it was actually near that proportion. So some women who've had difficult births in the past, or long labors, or labor goes on for, more than 12 hours or 18 hours or something, sometimes elect to have that. And some, when they're not going into labor, say, okay, we're at 39 weeks, we'll have a C-section at this date if the pregnancy doesn't. So anyway, so it's done for a number of reasons. Right, so the plug-in one, P hat plus or minus the 1.96. I'll just go ahead and put the numbers in because we wrote down the formula before, so it's 0.309 and 0.309 times 1 minus that 0.691 over 1,000. Right, with this sample size divided by 1,000, we should be pretty tight there. So it's 0.309. This margin of error on there is 0.0209, or sorry, 0.029, so less than a 3% plus or minus margin of error. So it comes about to 0.280 up to 0.338, right? So we'd be 95% confident that the proportion in the population of this type actually having C-sections would be something like this. Right? In R, right, I'm done. Right? There's a proportion test. Here are the arguments that are in it. You put X and N, and you can put a null hypothesis p-value. It's not a p-value, it's a value of P. Right? Confidence level, if you wanted something. You can do confidence intervals, one-sided or two-sided, and so on. It also has this thing called correct, right? So it does a continuity correction, where we're going from a discrete distribution to a continuous one, and matching up those probabilities at points versus area. Sometimes it's good to offset that by a half. So details aren't critical right now, but it's called a continuity correction. And so the proportion test, as we do it with our X and N, it gives this confidence interval, which is close to, but just a little bit different. Because before we had 0.280 up to 0.338, and this would round just a little bit differently in the third decimal place, right? You can take out that continuity correction, and you get this, 0.281 up to 0.338, which is very close to ours. It would differ. We had 0.22280, so it's just a little bit different because it's using this slightly different method, but essentially nothing particularly different there. What it's doing is, if you kind of go down here, it has this reference to Wilson in 1977, and so it's using that slightly more advanced formula that doesn't require only plug-in, but actually solves that polynomial equation. So anyway, it does something just a little bit different. But that's and it gives a confidence interval here. It also does hypothesis test. Now, it clearly rejects, the default is that the probability is 0.5, right? And that's clearly rejected because the standard error is quite small and we're at 0.309, so we're nowhere near it. But a more realistic hypothesis test for a proportion would be based, say, maybe on past information. Maybe in a previous year, 32% of women had cesarean sections. Women that are under these certain birth conditions without undue complications and singleton term births. Right? So we can set up a null hypothesis saying that things are the same, right? P equals 0.32, and the alternative that P does not equal 0.32. So then our statistic becomes, right, this is the thing that gives us our standard normal in larger samples. But under the null hypothesis, right, we put in the P0 here, right? And so that will give our Z statistic. Right? So we're going to have 0.309 minus 0.32, and then we don't have quite as much of a complication like for confidence intervals, where we have this unknown P that's bothering us. Here we've said what it is under the null. And if we do that statistic, it's negative 0.73. It's negative because our number is less in this survey than it was before, right? And so that's not unusual, right? It's not more than 2 standard errors out. So in this case, do not reject H0. And so the sample doesn't provide evidence that things have changed from 32%. The sample does not provide convincing statistical evidence that P is not 32%. So it could still be the same. And then in R, with this proportion test, you can give it the null hypothesis value test, and it gives us a p-value, it gives us a chi-squared statistic here. It does something just a little bit different. That chi-squared is like our z-squared. It's actually the square of our z-value. And so our z-value that we had was 0.73, or negative that. If you square that, you get 0.53, which is about the same. So let's see, let's go 0.309 minus 0.32 divided by the square root of 0.32 times 0.68 divided by 1,000. We get, oh, my number was a little bit off, I guess. And if you square that whole thing, you get the 0.556, which is the same as this chi-squared value, right? And so the probability that anyway, it gives a p-value that's not significant. Our confidence interval includes 32, and so we don't reject 32 because our p-value is there, right? There are some ways to, well, anyway, that's enough for now with these sample sizes, right? But we could have 2 independent samples, right? If we have 2 independent samples, right? We have samples from 2 groups, 2 locations, 2 populations, men and women, 1 person group of smokers, 1 group of non-smokers, right? So somehow we have these 2. Maybe they're randomized to these 2 groups, but maybe they just exist this way in nature and we get data from them, right? So maybe it's randomized and maybe it's not. So we have statistics for these 2. Our interest in this case is the difference between these. Depending on context, you might phrase it the other way, P2 minus P1. If P2 is the second time period and you do P2 minus P1, then a positive value means increase over time, and a negative value would mean decrease over time. So sometimes you take the difference, one group versus minus the other, to be kind of strategic. So it's a little easier to tell the story about it, right? But assuming that these sample sizes are not too small, and the expected number of failures and successes in each is probably about 5 or so, then P1 hat minus P2 hat is approximately normally distributed, with P1 minus P2 as the average. And then the variance of the first one is P1 times 1 minus P1 over its sample size. If they're independent samples, you add the variances, so it's P2, 1 minus P2 over N2. And then this, if you want to emphasize that that's the standard error, you can take the square root of the standard error here, right? So the standard way to make a confidence interval for P1 hat minus P2 hat, or the confidence interval for the mean, confidence interval for P1 minus P2. We're going to take P1 hat minus P2 hat, our difference of sample proportions, plus or minus 1.96. And then, there's a Wilson version of this too, but typically people just plug in those values. And unless the sample size is kind of smallish, it's not going to make a whole lot of difference. The other place that things kind of break down is when P1 or P2 get close to 0 or 1, because at the extremes, then you have very few failures or very few things. And you're trying to fit a normal curve over something that's all bunched up at one side. And it doesn't work so well. Right? So P1 hat, 1 minus P1 hat over N1, plus P2 hat, 1 minus P2 hat, right, over N2. And we simply get a confidence interval there that describes where that difference is likely to be. Right? And so if we had two different time periods, instead of that 32 or whatever coming from just knowledge, like maybe you do have industry-wide knowledge of millions and millions of pregnancies, and so it was 32%, so, or that's a published number from government sources, right? If we have time period 1 and time period 2, and say in the first time period you had 1,200 women, and in this one you had 380 C-sections, and this one you had 1,000 women, and here you had 309. So in this one, the p hat 2 is 0.309, as before. In this one, p hat 1, I set it up so that is 0.317. That would round to 0.32. So what's the difference of, well, if I do P1 hat minus P2 hat, right, is going to be time period 1 minus time period 2, 1.96. And we're going to plug in the different things here. If you plug in the numbers to the formula, anyway, we'll just save a little bit. The standard error ends up being 0.020, right? The interval that you would get when you would plug in all those numbers is like negative 0.031. These numbers, right, 0.317 minus 0.309. This is 0.008 as a difference. Right. So less than 1% as a difference between those rates. And this interval, right, ends up being like this. So we'd be 95% confident the difference between the two time periods is somewhere between 3% and almost 5%. Right? 3%, one is, that the first time period is lower by 0.031, up to the range that it's bigger by 0.048. And the best estimate of where the difference is a difference of 0.008. So it seems to have changed very little over that time period. Maybe you take a longer time period, bigger reform in medical practices, bigger reform in insurance practices, and so on. And it might change, right, for a bigger thing, right? But we could also do a hypothesis test, right? So we could test whether P1 equals P2 versus an alternative that they're not equal, right? Now there's just a little change in this, right? Because if P1, P2, but under the null hypothesis, they have some common value of P, right? And we got to plug something into that standard error formula for the proportions. And if the null hypothesis is true, it doesn't make too much sense to do separate estimates of those, so we're going to put the data all together. If we had N1 from one group and N2 from the same group again, same common values of proportions, we would just pool it together. So we're going to do a common estimate of this, add the successes together, add the trials together, and get that one. This is equivalent to taking a weighted average of the two individual estimates, where the weights are proportional to the sample sizes. If they're the same p, you're going to put them together, and the one that has the bigger sample size is going to count more. So we can evaluate this with a z statistic. We're going to take p1 hat minus p2 hat. Now, minus 0 under this scenario, right? Because if they're the same, the difference is 0. You could imagine in some cases where you've seen a 3% growth or a certain amount of change, your kind of, investments and things might have a sort of industry standard, like you're matching the stock market growth over time or something like that. So you might have a non-zero value there. But then the standard error gets reduced to p hat, 1 minus p hat. And the first one's divided by n1, and the second one, we'd have p times 1 minus p divided by n2. But because they're the same, you can pull them out and you do the square root. If you plug all these things in based on this example, you kind of skip writing out a lot of details. P hat 1 was this was kind of halfway between those two numbers from before. And so this statistic, 0.317 minus 0.309, and then our common p, 0.313, 1 minus that's 0.687, and then we have our two sample sizes, which are nice to have that size. And the square root of all that. And we get a z-value in this case of 0.40. Not a very extreme one, as you might guess from the confidence interval that was right centered around there. And then also that gives our hypothesis test there. This proportion test commanded R, I won't make sure that there's some time to write that down if you want. But the proportion test in R can do that, right? You put in a vector that has the different x's, and then a vector that has the different n's, and it does it for you. The default is 0. So proportion test, we can put, or I was going to show x and n. X, the vector of counts of successes, or some other versions of that, and x, a vector count of trials. So one number is a vector of length 1, so that's what we did before. And now we have one of these 380, 309, and then 1200 and 1000. And it gives an interval, right? It gives a p-value from a chi-square, or p-value from a test. This should be about equal to our z-value squared. Right? Our z-value we got was 0.4, so the probability that you're bigger than 0.4 or under normal is that. Is 0.4, so there's 34% above that. And if we double that for a two-sided test, that would be the p-value. So about 0.69. This was a little bit bigger. This had this continuity correction. So if we take that out, do we basically get equals false? A p-value of 0.699, and that's pretty close to what's there. They might be using that Wilson one or rounding a little bit differently, but it's basically the same. And these do not look different, right? So for many of you, right, you've seen things for estimating proportions, from introductory statistics to other things. This just presents it much more fast. Sometimes we estimate not the proportions themselves, but an odds ratio. An odds or an odds ratio. And so how does this Odds ratios are used in medicine, in clinical trials. The odds for getting a disease, getting better versus not, comparing one group to another. So probability for one group is between 0 and 1, and for the other group is between 0 and 1. So these are probabilities. Right. Odds, right. Take the ratio of P1 over 1 minus P1, right. The probability of, and so what's the range of those? I mean, they still can go down to 0, but because you're dividing by 1 minus P1, as P1 approaches 1, the limit of that becomes an infinity. 0. So you can report things on the odds scale. Right? Odds would be used in betting, right? So things like a 2-to-1 odds are, in like horse track betting, odds of 2-to-1, or sports betting. That's often translated in, well, if you add those up, it's like a 2/3 over 1/3 type of thing. So the odds are 2-to-1 in favor of winning. So there's, the odds, 1-to-4 for something that's less likely to happen. Could be translated into probabilities as kind of 1/5 over 4/5. So the odds are 1-to-4 in there, right? And so on. So the long shots in horse racing are the 1-to-20 or 1-to-40, bets that something's going to happen. And then an odds ratio is the ratio of odds. Right? So odds ratio between these would be the odds of the first group, right, over the odds of the second group. So let's call odds ratio, the book gives us a letter phi, right? So phi equals 1 means, right, equal odds. Right? P1 and P2 can be very different from 1/2, but if they're both 1/3, then you get this as 1 and equal odds. Right? And so some of the tests about are the proportions the same can be translated into questions about is the odds ratio 1 or not. Right? Equal proportions means odds ratio of 1. Right? And instead of actually dealing with the odds ratio, right, this thing again, you're taking a ratio of something between 0 and infinity over 0 and infinity, we still get a possible ranges of this thing between 0 and infinity. What's often reported are the log odds. So taking the log of this, right? So the thing that will show up in medical reports and things are the log of the odds, log odds ratio. So the log of this phi. Did we put a new symbol? No, it doesn't have a separate symbol for that. And so the ratio, the range that you can have for this is something negative infinity to infinity. So it stretches this 0-1 thing that's restricted out to something that takes up the entire real line. And so that's important, will be important when we start thinking about predicting odds. Right? If you have a bunch of x's and a linear equation that can produce numbers, prediction numbers between negative infinity and positive infinity, we can relate it to that, right? Instead of trying to fit everything onto the 0-1 scale and dealing with that. So this transformation stretches it out. And so log of 1, of course, would be 0. So a log odds of 0 means there's no difference between the groups. Right? So we have log of this is what we're interested in. Right? And so we need to estimate it. And then we need a confidence interval and a hypothesis test for this thing. Right? Estimation is not so bad. right? Because this is log of P 1 over 1 minus P1, P2 over 1 minus P2, right? You might see it written as P1 times 1 minus P2 over P2 and then 1 minus P1, right? Getting rid of the ratio over the ratio and just writing it like that. So to estimate that whole thing, we can just plug in the sample estimates as the traditional thing. Yes?
Just to clarify, that's the log of the entire
Yep.
fraction. The entire
Yep, yep.
fraction.
That'd be the log of this whole
Okay.
thing, right? And if you want to estimate all of that, I'll put little kind of hats on all of this stuff here. If we want to estimate that, we just put the sample proportions in there. Log of P1 hat, 1 minus P1, P2 hat, and then P2 hat, 1 minus P1 hat, right? You just put those in things. So we have our estimate, right? But we want a confidence interval for that thing, right? You might see this written slightly differently, right? P1 hat, for instance, is x1 over n1, and 1 minus P1 hat is n1 minus x1 over n1. So it's x1 over n1 minus x1. So it's a ratio of the number of successes over number of failures. And so this thing is the log of x1 n2 minus x2, and then this is x2 here, and this is n1 minus x1. So you might see it written in terms of the counts rather than in terms of the proportions, but it's just emphasizing when you're taking those ratios, you don't necessarily need to divide everything by n1 to produce this ratio. So we can estimate it, but what's the variance? Well, if sample sizes are reasonably large, right? So n1 and n2 are big enough, are like each greater than the expected number of failures and successes. N times P1, n times P and n times 1 minus P for both groups is greater than 5 for each one at least, maybe bigger, right? Then the log of this P hat actually is approximately normally distributed. It's in large samples, it's the log odds ratio. That's not the mean, that's the kind of asymptotic large sample mean. It has a bias to it because we're taking ratios of things that are nonlinear. This is nonlinear transformations. We don't get unbiasedness. But in large samples, the bias goes away. And the variance is like 1 over n1 p1, 1 minus p1, plus 1 over n2 p2, 1 minus p2. And this thing, if you write it out, can also be written out as n1 p1 plus 1 over n1, 1 minus p1, plus 1 over n2 p2, plus 1 over n2, 1 minus p2. For that variance. And this is often presented a slightly different way, that if you have group 1 and group 2, and then maybe this is a positive outcome and a negative outcome, so you have your two groups and 2 responses, and then the number of things you have, the number of counts in the 2 by 2 table is like that, so that A plus B is what we called N1 before, and C plus D is what we called N2 before. Right. Then the estimate of this variance, the variance of this log theta hat, the estimate of that variance, plugging in estimates for P1 is like computing 1 over A plus 1 over B plus 1 over C plus 1 over D. But for a year and a half, I was called a visiting or an acting assistant professor at Stanford, that they needed somebody to teach introductory statistics and things. And so I talked to Brad Efron. He said, why don't people just put everything as A, B, C, D? It's so easy to keep track of the counts and things. Why do people use subscripts? X11, X12, X21, you know, it confuses people. Why don't you just use A, B, and C, and D? So anyway, that would be the estimated variance. So where does this come from? Right? How do we get this? The other ones, the binomials, come from figuring out the means and variances from a binomial distribution. So it's working with the probability distributions. Where does this error come from? Does variance come from? How do we get it? Okay. What is a Taylor series approximation? To the log of phi hat. Right. And this was the log of P1 hat, 1 minus P2 hat, P2 hat, 1 minus P1 hat. So there's two parameters. P1 and P2 that are there, and you can, if you knew P1 and P2, the log of this thing is this function of these two parameters, right? And so you can do linear approximation to that complex function around the real value. So how does it go? The log of phi is approximately equal to the log of phi. Oh, phi hat, sorry, is approximately equal to the log of phi plus, there's two terms that get put in there for the approximation, right? So to approximate this thing about this, right, you would have P1 hat minus P1. Right? P1 hat is close to P1, and the multiplier you do here is related to the derivative. Is the derivative of phi with respect to P1. Right? That's the multiplier there that's doing this approximation. Plus P2 hat minus P2. And these are really partial derivatives. In there. So just like if you had some function here and you wanted to approximate it, right? You would say, well, it's about equal to the function, evaluated at the things, then we take a derivative and say it's kind of like this line here, right? And we're doing this in the two dimensions, kind of the surface, right? So what do these end up things being? The log of phi plus p hat minus p. Right? And what is this thing? Maybe I'll go to the next page to get it. So the log of phi, log of P1, 1 minus P2, P2, 1 minus P1. This all could be log of P1 plus log 1 minus P2 minus log of P2. Because it's in the denominator, it becomes negative. Right? Minus log of 1 minus P1 right, is there. So the logs break out. Right? And so if we differentiate, call this thing with respect to P1, right, we get 1 over P1. And then there's 1 over 1 minus P1 here. Where there's a negative, when we take the derivative chain rule of 1 minus P1, we get another negative, so it becomes a positive. And what's this thing? well, P1, 1 minus P1. You put it under a common denominator, you have 1 minus P1 plus P1 in there, and it just kind of reduces to that. So that's the derivative with respect to P1, with respect to P2, yes?
So is that a partial derivative? I can't tell if that's a D or an M.
Yeah, it is really a partial derivative because there's two functions there, right? So it's really a partial because you could do P1 or P2.
Yeah.
If you do the partial with respect to P2, I think you're going to get negatives, right, in there. It's going to end up being negative 1 over P2, 1 minus P2. Will end up being in there, right? It'll be okay. It will come out in the end, right? So now if we go back to the other page, we can see what this thing is. Right? Oops, wrong direction. So this thing had P1, 1 minus P1 here. This one has P2 hat minus P2. And there's a negative 1 over here, P2, 1 minus P2. Right? That's in there. Right, so that's a linear approximation. Right. So, to this first order linear degree, what's the expectation of this approximation there? So, in this formulation, the log of phi is just a number, right? So if you really knew P1, P2, you could take the log, you could take the odds ratio, and the log odds ratio, and give me the number. Right? What's the expectation of P1 hat? Just P1, right? So this becomes 0, right? And expectation P2 hat is P2, so it's 0 plus 0 plus 0. So to a first order approximation, I'll put this down here where it's a little bit nicer. So to a first order approximation, our sample estimate of the log odds ratio is this, right? There's a little bias because it is nonlinear, but to a first order approximation, it works out well. So if you have large sample sizes, you get that as the mean. So what's the variance? Right. So the variance of this to a first order approximation, that's just a constant. The thing that's relevant for variances are P1 hat, P2 hat, these two independent proportions, right? So it's going to be the variance of this plus the variance of that. So that negative 1 that we had over here gets squared and goes away. And so let's see what we get. Right? So the variance of log of theta hat is approximately equal to, well, there's the variance of P1 hat, and we divide it over here by, right? P1, 1 minus P1, but when you do that, it gets squared. Right? So P1, 1 minus P1, all of that squared. There's the variance of P2 hat, and there's P2, 1 minus P2, all of that squared. But the variance, this part of it, right, is P1, 1 minus P1 over N1. So one of those P1s, 1 minus P1s will cancel there. And so we end up with 1 is P1, 1 minus P1 here. And we do the same thing kind of by analogy over here into 1 minus P2 over here. And so that's what the variance of this log odds ratio ends up being. So we could do an interval with that one. Right, so there's just a couple minutes, so maybe we'll come back Monday, maybe kind of look at one numerical example. You could look at that portion of the book. To do that, you're working on the homework that's due on Monday and thinking about projects. But if you look through chapter 18, we'll do a little bit more there with some of these things. But just to kind of summarize these, what we've been doing here at the end, many medical studies report things in terms of log odds. And practitioners are used to looking at odds or log odds. Odds near 1 means equal, log odds at 0 means equal. And so they report things on the log odds scales. This will be the natural transformation that we will use for logistic regression, or the log odds, not the log odds ratio so much. But we just take a very simple estimate of the log odds, right? But we want to know, do a confidence interval or hypothesis test about it. And so we need the standard error of it. And to do that, this is what the variance is going to be. So if we want to estimate it, we can plug in sample estimates of these different things, which ends up 1 over the 4 different things. Increase in that 2x2 table. We're cross-classifying based on group and outcome. And how did we get that? Well, it's this Taylor series approximation. Essentially, it linearizes this complex statistic. Linearization, Taylor linearization, gets used all over in statistics. There's a lot of nonlinear estimators, and the first line approach to getting variances and expected values to linearize it. So it's a good technique to get from mathematics. And so we figured out, that and the variance. And so having a variance formula, then we can do a confidence interval. We'll do a numerical example on Monday. All right. Have a good weekend.
Thank you. So I got your email.
Oh, yes, okay. Yes.
I'm thinking maybe next Friday on some of the student material.
Okay.
I don't know if you want to meet to
Sure.
go over stuff a little.
Sure. Yeah, right. So we'll do some lecture on Monday, maybe meeting on Wednesday be enough time to
Yeah.
meet on Wednesday?
Yeah, we can meet on Wednesday. I've got a lot going on before then, so
Okay.
that'll probably
Okay.
give me enough time.
All right. Cool.
Yeah.
Yeah, we can meet on Wednesday, and so whether you do, part of the, there's a different version of this for small sample sizes. There's
Okay.
a version for correlated proportions. So one of those two options, or
Okay.
yeah.
Yeah.
But it seems like November is just flying by.
Yeah, it does. I thought it was going to feel really long with Thanksgiving being really late this year, but it definitely does not. It is flying by. I can't believe there's pretty much 2 weeks left before finals.
Right. Yeah. Next week, then Thanksgiving week,
Yeah.
and then one more week, and then it affects how things go. So like in my 252 class, I could have one more assignment due the last week,
Yeah.
but it's such a gap. I mean, I'm thinking about just kind of forgetting the last assignment and having students
Yeah.
review and do projects. So
Yeah.
so it kind of changes how it ends up in the end. So.
Yeah. I ended up with lots of papers that last week, so
I think if you just did the process right,
it's different for me,
Right.
but anyway, have a great weekend.
You too.